Alright, if you go to the practice problem sheet that I put up, I don't even know what it's titled. It's practice something, weak acid, strong base, but the third problem in it is a weak base, strong acid. Gonna go through these. Gonna take a little more time on the first one. It has only 3 phases. The second one's got 5, so hopefully we can set up a pattern among these. I've very rarely worked with weak base, strong acid titrations, and that's why I'm doing 2 examples of weak acid rather than of weak base. So we got acetic acid again. I remember memorizing Ka equals 1.8 times 10 to the negative 5th and pKa is 4.74 in high school. Couldn't remember why, and it's because acetic acid, the stuff in vinegar, is almost always your weak acid. So I feel like ammonia is always your weak base. So let's look at these. Acetic acid is a weak monoprotic, blah, blah, blah. This is nice. 1 liter, 0.0179 molar acetic acid, so my moles are just gonna be 0.0179 moles HC2H3O2. Good. That's how many moles I've got. So when I'm doing my comparisons, that's what I'm going to use. And this was weird. We're not using liquid sodium hydroxide. We're using solid. Solid sodium hydroxide looks like it should taste good. It's shinier versions of Dippin' Dots. Don't eat it. So what's going on here? This was my equation for the breakdown of the acid. That's the original one I would use to calculate the original pH. So this would be pH to start. Not a question in here. I would normally need that because usually we start with the pH to start. So we're adding 0.0107 moles of NaOH. So the equation I want here is this acid. Let's do the next one. We're going to add some amount of OH, and we're going to get, well, it's going to take that proton, C2H3O2 minus, and it's going to make some water that we don't care about. Cool. Yep. So we're going to ignore the water we don't care about. Well, we started off with 0.0179 moles here, and we added 0.0107 moles here. Well, that's going away. It's taking this with it, 0.0072 moles of acid. What's going to happen from this OH? It's going to make 0.0107 moles of base, C2H3O2 minus. Very nice. It's a buffer system. We haven't added enough to get to the equivalence point yet, so it's a buffer system. So I want pH equals 4.74 plus the log of, which is my base? 0.0107. It's the one without the proton. And 0.0072. There we go. When I put this in my calculator, please check me. The website I got this from had a different answer, but I did it like 4 times, right with their math. I got pH was 4.91, which is going to make sense because I added some base, and it would be different there. Okay, and I am over half the equivalence point, so I should be above pKa. Nice. Oh, here we go. Calculate your pH of a solution after the addition of 0.0179 moles of NaOH. I'm at the equivalence point now. Going to take this down. You can pause and copy if you need to. Take that down. That is one nice thing where it has to sit on the board at school. And you can pause and copy. So I'm at the equivalence point. When I'm at the equivalence point, I do that base equation. I got to do my base equation here, and I'll need Kb, which also now goes with that in my brain. One of those things I've just done too many times. Yeah. So I've made all of my C2H3O2. So what I was looking at here, let's just do this real quick. I would have started off with HC2H3OH, O2, and I would have added OH. And I've got the same amount of each. And I'm making C2H3O2 minus, and water no one cares about. So if I add this much base, it neutralizes that much acid, and in the process makes that many moles of the acetate ion. It makes that many moles of the conjugate base. Now, that's what I'm going to be concerned with. I'm just going to use my conjugate base. What do conjugate bases do? So this is at the equivalence point. I need KB, the equation where I make the conjugate base, and then the equation where that conjugate base reacts with water. Why do I care? We don't like water. Because it then remakes the acid and OH minus. Good. So I know my concentration of acetic acid. It's going to be my number of moles and my total volume, which looks like a liter this time. So I'm able to say, that was so nice of them to use a liter, 0.179 molar. And remember, we're always ignoring X at this point. We've given up on X. So it would be, if I were filling in the ice chart, minus X here, and plus X here, and plus X here. So, I don't need the minus X here. This is my base. What I come up with from here is also not going to change, just like my initial pH. This is always going to be Kb, X squared, concentration of the conjugate base from the acid on the bottom. What this is going to give you, and for me, on this one, and you can solve through it, spend your time on that, I got 3.16 times 10 to the negative sixth. This is going to be my concentration of OH minus. So to get to my pH from here, 14 minus negative log of that, and the pH I got from 14 minus the negative log of that, which you can do, 8.50 was my pH here. Is that expected? That's basic but not crazy. And that would make sense for the equivalence point of a weak acid strong base titration. pH of the solution after, ooh, that's lots of moles. That's lots of moles. And this is where I said, I bet I can do this more quickly than I did in the example on the packet, because that worked in circles. We're going to condense that a little bit. That one showed you all of the steps, and as I was reading through it, I'm like, I typed all of these steps. I really didn't need to, because check this out. If I have, this is past the equivalence point. I just have base. I have 0.0286 moles of OH that has slurped up 0.0179 moles of acid. That leaves me 0.0107 moles of OH minus. Now, because it's in 1 liter, which was lovely of them, there's my concentration of OH minus. Past the equivalence point, it's sort of like what we did here versus what we did in the original practice problem was just skip the, hey, we can ignore X. We ignored the small difference in concentration that came from the stepwise calculation. Basically, moles of base minus my total number of moles of acid gives me a moles of base. Normally, the calculation to go from moles to molarity, I'd have to show dividing by liters, but it was 1 liter. Again, lovely of them. So I'm doing 14 minus negative log of that to get my pH, which this is past the equivalence point. It's what I said about a blown buffer. I got 12.03, a very nice basic pH. So that's expected. And that was around 1. I do have around 2. I will probably go through it slightly quicker because there are more parts, but another video coming up.